Hello, this is part 2 in our video series about old school wireless communications. For those of you who also viewed part 1 in our video series, welcome back. For those who are new viewers, we'd like to welcome you too and suggest that you watch the part 1 video to get a more complete understanding of how wireless communication worked back in the very early stages of its invention and use. So a quick review from part 1. Wireless communication involves the transmission of electromagnetic waves through the air from a transmitter to a receiver. This was true back in the late 1800s and is still true today. Cell phones, Wi-Fi, radio all use electromagnetic waves to communicate. Back in the late 1800s, early 1900s, they used Morse code. They would send a short batch of waves to indicate a dot and a longer batch of electromagnetic waves to indicate a dash. These electromagnetic wave dots and dashes would be picked up by an antenna on the receiver side. You could then either have a person who knew Morse code listening in and writing down the message as it came in, or, as we'll demonstrate in our video today, this could be done with a machine called a Morse writer, as in Morse code. So this is our Morse writer machine. The Morse writers they had back in the early 1900s were made of brass and were a lot prettier than this one. But this one works pretty much the same as they did back then, and it does a pretty good job in demonstrating the principles of how it works. And here it is in action. As we receive the electromagnetic wave dots and dashes sent by our transmitter, our Morse writer writes the dots and dashes to a paper tape. Our Morse writer is a pretty basic machine. We have a continuously moving paper tape that's driven by a small electric motor and a gear train. The actual writing is done by a pen attached to a pivoting arm. The pivoting arm is powered by an electric motor. When we receive an electromagnetic wave from our transmitter, the motor is turned on, which pushes the pen down on the moving paper tape. Because the paper tape is moving, this leaves a mark on the tape. If we receive a longer batch of electromagnetic waves from the receiver, the pen is held down on the moving paper tape for a longer period of time, which makes a longer mark, which represents a dash. If we receive a shorter batch of electromagnetic waves from the transmitter, the pen is held down on the paper tape for a shorter period of time, which writes a dot. So that's how our Morse writer works. The only question remaining is, how does the Morse writer know that a signal has been sent by our transmitter and that it needs to write down a dot or a dash to a paper tape? That's what we'll talk about next, and it's actually one of the more interesting parts of this project. So let's go back to the beginning and look at our transmitter. Our transmitter is a Tesla coil. The Tesla coil is capable of creating a spark of very high voltage alternating current. Thanks to a scientist named Heinrich Hertz back in the 1870s, we know that a very high voltage alternating current spark will emit electromagnetic waves. And these are the electromagnetic waves that we will use to communicate Morse code to our receiver and our Morse writer. So at the point where our electromagnetic dots and dashes are created, we are dealing with a lot of electrical energy. However, by the time the electromagnetic wave has reached our receiver, this electric energy has dissipated significantly, and we will not have enough electric energy from the electromagnetic wave to run our Morse writer. In order to get the stronger current that we need in order to run our Morse writer, we use something called amplification. And this picture here illustrates conceptually how amplification works. So the energy in our electromagnetic wave may not be strong enough to run our Morse writer, but it is strong enough to turn on a switch. When the switch is turned on, that allows a stronger current to flow, and that stronger current is strong enough to run our Morse writer. So again, this picture just represents conceptually how amplification works, and we don't really use a light switch to turn on the power to our Morse writer. But we do need something that can perform the function of a switch. And this was also something that Marconi and the other early pioneers of wireless communications had to wrestle with. And they came up with all sorts of inventive, convoluted solutions and devices to perform this switching function. Now I know this video is about old school wireless, but we're going to cheat a little bit here and we're going to use a transistor as our switch. So conceptually and functionally, this transistor works just like the wall switch we showed earlier. We have a weaker current from our electromagnetic wave. This turns on the transistor, and this allows a stronger current to flow through the transistor and to our Morse writer. So eureka! We've done it. We've completed our old school wireless communications end to end. We started with our Tesla coil transmitter. The transmitter creates a high voltage spark which emits electromagnetic waves. The electromagnetic waves are picked up by an antenna at our receiver and amplified. Finally, our Morse writer writes the Morse code message to a paper tape. So thanks very much for watching. I hope you enjoyed our short video series on old school wireless communications. Thanks again.